Okay. Good afternoon, everyone, and thank you for being here today. We're excited to present to you our thesis graduation project. Namely, our product is called SightSync, and the project was supervised by Dr. Mohammed Shalain and Dr. Mohammed Sidi. But before we present our product to you, we wanted to tell you more about the motive behind the idea itself. So, having been exposed to AUC inclusivity mindset for the past 4 years and constantly working with people from different backgrounds, abilities, and stories, we were inspired to use this project as a chance to give something back. So, we wanted to create a system that serves the same purpose that AUC served for us, namely a system that nurtures our souls and reignites our faith in humanity and the world around us. And as computer science and engineering students, and I think everyone here would agree, that there is one thing we heavily rely on and cannot live without, which is our ability to access our technological devices. Because they're our primary source to the world, and they're our main gate for knowledge, education, development, and work. So losing them would mean that we're losing our main access to the world. So we can't imagine being in the place of those with disabilities who can't experience technology as we know it. Instead, it's always been a locked door for them. And while we're seeing great improvements in... Oh, okay. We're sorry for this? Yeah. And while we're seeing great improvements in the physical accessibility area, for example, there are ramps, elevators, and accessible classrooms, we noticed that there's a huge gap in the technical accessibility area. And that did not sit right with us. When we looked into products, into existing solutions of assistive human-computer interaction tools, we noticed that there are 4 points that keep coming up again and again. First of all, price. The devices cost as much or even more than the computer itself. Second of all, lock-in. The devices are connected to one platform, one operating system, or even one company. And power and connectivity. They demand strong hardware, stable connectivity, or even the cloud just to function. And also bulky hardware, they stand out that they label the user as different. And this is exactly what SightSync is aiming to solve. So our product, SightSync, where your vision drives the system. It's a low power, I don't know what's wrong with that. Okay. It's a low-power, offline, affordable, assistive eye tracking gadget designed to let users control a computer using only their eyes while blending seamlessly into a normal setup instead of looking like medical equipment. When we looked at the market, we noticed that there are 3 main categories of existing solutions. First of all, high-end assistive eye gaze devices. For example, Eye Gaze Edge. These are very accurate, but they're very expensive and hardware-specific, and they're mostly used in specified clinics or centers. Consumer and research eye trackers, for example, Tobii Eye Tracker 5, but these are mainly designed for gaming and UX research. And they're also they require powerful PCs. There's also the DIY or webcam-based software, for example, GazePoint. These are affordable, but they also require a full setup, like a full computer and a high power consumption. And they're not really packaged in a discrete, dedicated. They're not dedicated to be assistive devices. So this is why we designed SightSync to sit in a different spot on this map. It's significantly more affordable by using accessible and embedded hardware. It's device agnostic, allowing users to connect with different systems instead of locking them into one system. It works completely offline and with minimal power consumption, making it suitable for low resource environments. And it's also, most importantly, visually discrete because it's a very clean, can we please show the gadget? It's a very clean, and small gadget, as you can see, and it blends seamlessly into the setup. Okay, and we also designed SightSync with real users and places in mind. For example, some of our target users include people with motor impairments, those who can see and think clearly, but they're unable to interact using the mouse or the keyboard. For example, people with spinal cord injuries, ALS, cerebral palsy, and much more. Also those with temporary limitations, those suffering from an injury or recovering from a surgery, who still need to work, study, or just have fun. And also, we're planning on selling our product to companies, universities, and schools to enhance workers and students inclusion, rehabilitation centers and hospitals for patients, NGOs and community centers for people working in low-resource environments where assistive high-end devices are simply just not an option, and also home environments for families who want a plug-in solution instead of an entire setup. So in short, SightSync aims to take the eye tracking out of the niche, high-cost medical corner and bring it closer to where it should be, a quiet, invisible bridge that helps more people participate fully in the digital world. Now, moving on to our demo.
Now, this is the demo of our project. At the beginning, you will notice that I'm controlling the mouse using my eyes. So you'll notice that I'm looking downwards and the mouse cursor is looking down, going down. My target is Chrome browser. So once I'm on it, I will blink to click the mouse. Then I will go to the search bar. Then I'll click on it to focus on the search bar. Then I'll do a left blink to open the virtual keyboard. This allows the user to write what they want. So for example, if I want to go to YouTube, I will write YO, then I'll click enter. Once YouTube loads, I'll go to the search bar of YouTube, then I'll blink to focus on the input. Now the control is back to the keyboard, and I will type CSE AUC. So the way it works is I control the keyboard using my eyes, and whenever I'm on the key that I want to type, I blink. Our keyboard is highly customizable, so it has a lot of features such as copy, paste. You can open the task manager, you can control its size, etc. And you can control the position of the keyboard on the screen using the 4 green arrows at the bottom. Our system also ignores natural blinks. So you will notice that when I blink quickly, it doesn't register that as a blink. So it doesn't click the mouse. Now, for the setup of the Pi, the user must be around 60 centimeters from the Pi camera. So once I'm done typing what I want, I do another left click to close the virtual keyboard. Then I select the first option. After that, I raise my eyebrows to enter scroll mode. This allows the user to scroll through the videos without controlling the gaze. Now, moving on to the full pipeline, it starts by taking an image of the user using the Raspberry Pi camera module. This is sent to the Raspberry Pi using the serial connection between them. Then the image is passed to the 2 models, the face detection and the gaze. Then they estimate where the user is looking. This data is sent by the Pi to the PC. Then the PC handles the mouse movement and the blinking. Now moving on to the hardware diagram. So we capture an image using the Raspberry Pi camera. It has an 8 megapixel sensor. The image is sent to the Raspberry Pi where all the processing happens using its quad-core ARM Cortex processor. Then it's sent to the PC using a micro USB connection. Now moving on to the software level view.
Okay, now on the software level view, this is the pipeline that powers all of SightSync. The process first starts by capturing a raw RGB image. This image is then sent to the face detector, which takes the frame and tries to find where the face is. Right, so the face detector is built on the YOLO-X architecture and uses some proxyless NAS backbones to improve the accuracy of finding the face. It's trained on the wider face dataset, and it takes the raw image and outputs face bounding boxes. Then, moving to the next part of the pipeline, we take the output of the face detector, which then goes to the facial landmark extractor. The facial landmark extractor uses the MediaPipe face mesh, which is a lightweight regression plus mesh decoder. It was trained on the internal Google dataset. It takes the face, the face that was cropped from the image, and then outputs 468 to 478 landmarks. So where the eyes are, where the mouth is, where the eyebrows are, and all that. Next, after that, the pipeline is split into two streams. The output from the facial landmark extractor goes to the gaze estimation, which uses the AgeNet architecture, plus again the Proxylus NAS backbone. It was trained on the ETH dataset, and it takes the input of the face, which then also crops both the eyes and outputs the gaze direction, or pitch and yaw. Now, looking at the other stream, you'll see that the facial landmarks output also goes to the blink detection. Now, the blink detection doesn't use a model. It essentially just draws points on your eyes, on your eyebrows, and on your mouth, and calculates the distance between them. And we have set a threshold for each one to either detect a blink or a toggle. So for example, the EAR, the eye aspect ratio, it can either detect a left blink, a right blink, or a keyboard toggle. The MAR, the mouth aspect ratio, which stops the communication with the pie, which then stops the mouse entirely. And the last one, the EBAR, the eyebrow aspect ratio, which toggles on scroll mode or stops. Then both outputs are sent to a serial queue. This serial queue, he has the pitch and yaw values and the signals sent from the blink. Now the blink has a higher priority than the gaze, I'm sorry. Because the gaze is continuous, while blinks happen occasionally. Then finally, this queue is slowly popped into the PC, which then moves the mouse and does the signals. Now let's see what the user sees. First, after plugging in and mounting the camera, the user will see the calibration system. It's a 15-point system that helps the gaze model recognize gaze patterns of the user. It takes 100 samples per point, and it takes about 1.5 minutes to calibrate. Then the user can start using the system right away. They can do eye movements, toggle the keyboard, blink, and all that to navigate around their system. And this is the UI when they toggle the keyboard, and this is what appears to them. And the system is very simple and non-intuitive.
Okay, so let's talk about how did we test our system. So first we began by unit testing, in which we tested the gaze estimation module alone and the blinking logic alone. Then we moved on to integrating both of them and testing on our laptops using the webcam. Once we reached the accuracy that we wanted, we moved on to integrating our software with the hardware, which is the Raspberry Pi. Finally, after a lot of trials, we achieved what we've wanted, the full pipeline, taking the frame using the Pi camera until seeing the corresponding movement on the connected device. To ensure that our system is accurate and reliable, we asked 20 participants to test our product, and based on their feedback, they didn't face any difficulty in the setup or even in understanding how our system works. Next. Okay, so I'm sure some of you are wondering, why did we opt for a hardware-software solution instead of just going ahead and creating a software solution? When we were creating our product, we had 3 goals in mind. First, we wanted to create an energy-efficient product, and of course, with having accuracy in mind. So we were always opting for solutions that consumed less power and less CPU. The second goal was to have a unified camera resolution to ensure that we have the same accuracy across multiple devices. And finally, portability. We wanted to ensure that the user can plug our system into any device they would like to, and it should take simple steps, just plugging in the USB with minimal setup. So these are the goals that we wanted to achieve, and this is why we opted for a hardware-software solution. But I also want to note that we have a software solution available. Next slide. We were testing our theory, and we saw that when we ran our full pipeline on the PC, and when we ran it on the Pi connected to the PC, as you can see, when we connected the Pi, or we had the full pipeline on the Pi, it ran it consumed a very small amount of battery, and also very small amount of CPU and memory compared to running it on the PC. However, there also exists a software solution if someone would like to buy it, for example. Another thing that is very important to note is that once we connect the Pi to a laptop or a device, it's powered by the device. So we wanted to test how much power does it actually consume. So we found out that it consumes 5.6 watts per second, which is extremely, extremely slow compared to actually running the model by itself on the device. Yes.
As of today, according to the World Health Organization, there exists 1.3 billion people that suffer from one or more forms of disability. And according to the Disabled Hub Europe, this number is expected to double by 2030. And when we examine, we found out that 10 to 15% of those disabled people get access to the what exists on the market from products that enable accessibility and so on. And when we examined the market, we found out that the market is very fast growing. As we speak, it's at a cost of 23 billion USD dollars and expected to reach and even exceed $32 billion by 2030. And the paradigm is glancing clear. We have a huge growing market, yet we have very limited access. And so this is attributed to one main thing, which is the price. The price of the existing products is very expensive, as if we can see for the eye gaze estimation products that exist, they can go up to thousands of dollars, which is unaffordable to even families like here in Egypt, which live in lower to middle classes and in our region. And also, to worsen the situation, these products are very bulky. They require very fast and strong PCs, and also they require stable internet. And so at the end, you get a product that is clinically impressive, but not realistically scalable. And here where SightSync comes in. And so we are aiming to cut down the hardware cost, have an offline, reliable, accurate, low power cross device that's ready on the use, easy to use and set up, it doesn't attract attention to how it looks, and it comes at a selling price of just $80. And so for our business plan first, each unit costs around $46, split on the hardware and software. And then we want to start our first batch with 100 units, which will cost us $46,000. And we're also going to set a website and a domain for it, which is going to cost $300, have a marketing campaign for up to $1,000. And also we're in talks with distributors like BTech, Amazon, Shopify, and so on and so forth, to have our products ready to be sold on their website, which is going to cost about $800. So in total, we have a total investment of $69,000 and a total expected revenue of $8,000, which leaves us with an expected profit to up to $1,400. And so our product, SightSync, it can not only perform very well in the technical aspect, but also it can fit in a very competitive and very expensive market. It offers the solution, the very slightly semi-cheap product that goes in and fills the gap that exists in the market.
And so we would have achieved our desired empowerment outcome, which is to create a commercialized product. By designing SightSync to be low power, affordable, offline, and device agnostic, we position it to be a